It sounds like it does. Well, it's collaboration. That's, again, one of those things that I think traditional math classes lose is the spirit of collaboration amongst people. You know, plays well with others kind of thing. And I remember having a discussion a few weeks ago with some colleagues at a different school when I told them, yeah, I do a bunch of out-of-class assessments. Like, how do you know they're not cheating? And I said, God, I hope they are. And they're like, what do you mean? I'm like, well, what you call cheating, I call playing well with others. And they just like looked at me with this blank face. I'm like, wow, we're totally on different pages here. Like, you're training the next math class. I'm training people to actually go into the world and be able to coexist with people. And they're like, oh. And then we just stopped talking. We talked about rock climbing or something else. And I realized I couldn't communicate with them anymore about that. So anyway, I just had to. It's like, you know, you're great people. I can't talk to you about this anymore. What I want to do is kind of motivate where we're going next. It's tied to what we just got done talking about, which is linear modeling. When I say modeling, what am I talking about? Good! A graph, perhaps? An equation that generates a graph? That does what? Love that. What does the equation or the graph do? Say that again? A best fit line. What are we best fitting? Good! You got some data. You got some kind of cool pattern that happens in the world that you care about where it's going and what it's going to turn into. Then you generate data from that. And then you take a look at the data and you say, what does that data look like? Oh, it looks like a line. Let's find a line that goes through it the best and then use that line to do something. Fantastic, fantastic. What I want to do is talk about when that best fit isn't linear. So these are called the conic sections. These are kind of fun, actually, mathematically. If you take a cone, like an ice cream cone, stand it upside down and you cut it different ways, you get different shapes. It's kind of fun. It's kind of fun. If you cut it straight across the top, parallel to the base, you get what's called a circle, which I think anybody can. It's basically what happens. You cut a tree across flat. A tree is essentially a cone, essentially. So you get a circle. If you cut on an angle, as opposed to parallel, you get an ellipse, or sometimes I think an oval. We'll call it an oval. My son calls it that, an oval or an ellipse. Those are wicked fun to draw. If you ever have to put one of those on a fence, so if you want to make an oval cut across the top, I've discovered that circular cuts on like a fence door is usually a little too steep. A little too steep. Ovals look better, ellipses look better. If you ever want to do that, shoot me an email. There's a really cool way with a pencil, a string, and 2 nails that you could draw a perfect ellipse. Super fun. Kirsten's done it. Yes, very, very cool. Very, very cool. And then, if you let it tilt even more, so that the saw doesn't cut all the way through to the other side of the cone, you get either parabolas or hyperbolas. Hyperbola would be a direct vertical cut. I don't want to talk about that. I want to talk about parabolic cuts. And why would I want to talk about that? Because they're freaking useful. Check this out. This is a parabola cross-section. If you were to shine light into a parabola, parallel to what's called the, or perpendicular, I should say, to what's called the directrix, or parallel to the symmetry line. So symmetry line meaning you can fold the top down and the bottom would lay perfectly. That line of symmetry, if you shine light into, or you shine any kind of energy directly into it, parallel to that line, it bounces off and redirects right into what's this thing called the focus. Now, that has been exploited for centuries for its usefulness. Here's one way. You guys have seen this. Or you've not this, but you've seen things like this. Yes? Yes, you see them hanging off the sides of houses quite frequently. They're not quite as big anymore. Oh, some of them are, depending on what they're collecting for. But what's going on? What's going on in that parabolic antenna? Now, it's actually a 3-dimensional parabola. It's collecting data, whatever it is, whether it's a radio wave or a TV wave or a light wave, who knows what it is. But those waves are coming in essentially parallel to this line and then redirecting where? I'm guessing that thing right there, where it's then collected and sent into whatever the processing center is. But it's a way of getting all that data into one place rather than having to have a whole bunch of little things out and about. Yeah? Make sense? Yeah. Here's another one. I don't know if you can tell what's going on in that picture. It's a parabolic mirror. The dude's burning a hole through a piece of cardboard. Isn't that badass? This is not like you used to do when you were little setting the ants on fire. It's not that. That's a different kind of collection. That's the light coming through and then going out the other side. This is the light coming in and then bouncing back to the focus, which is out here. Notice how far away the focus is from the actual parabola itself. If you were to continue this parabola out, it would be out here. This guy is much further forward than the actual sides, which means you don't need much of the parabola to generate a lot of heat because it's all being sent to one point. Kind of amazing, actually, if you think about that. I watched, there used to be a show, this is way back in the day when I had a lot of time to watch television. There was that terrible show, Survivor, like the first reality show, which is such a joke. But then a bunch of scientists decided to have their own Survivor show where they dumped scientists on an island and had them collect trash and build stuff out of the trash and live off of that, which was really cool. And one of the dudes, I think it was a guy, could have been one of the girls, built a parabolic oven out of foil they had found washed up on the side and cooked stuff with it. Totally rad, totally doable. Parabolic reflectors. They used one to, oh please, David.
So this may be off topic, but with the reflector there, is there a relationship between the sides of it?
And where the focus is? Sir, yes. I'm going to back up here real quick. There's a lot of mathematics, which I'm not going to make you do because it tends to be a lot like that, but even more so, because it's not linear anymore, it becomes quadratic. There's a mathematical relationship between where that focus is and how far back this thing called the directrix is. The directrix is the other line you need to draw the parabola. So technically, the definition, this is a great question. I hope when I answer, I hope you don't mind it.
Yeah, no.
The definition of a parabola is, it's the set of all points equidistant from a directrix, which is this guy, and the focus. So if you take the directrix and draw a line from here to here and then here to here, that has to be equidistant for all points on that line and all points on the parabola. And so depending on how far you pull them or push them, that changes the shape of the parabola. So the further back you pull the directrix, the further forward the focus goes, and the more the parabola does, which is why the antennas you see are not curved like this. They're not curved like this at all. They're curved very, very steeply. Or I guess it wouldn't be steep. The way you guys learn about parabolas in Algebra 2, you probably call them shallow. The ones with the A values that were fractional, they opened up like this, like a very wide open flower. Those are the ones the antennas look like, which is why the focus is so far forward. It's so far forward versus being way back here, because those things have a very, very slight incline. And I think the reason is you're exposing more surface area when you make it three-dimensional. When you swing it out to 3 dimensions, you're creating more surface area to collect. So you don't need as much this way because you've got tons this way. That's a guess. I have no idea if that's right or not. It makes sense as, like, logically. Great question. Thank you. Do you remember? I think this was the I don't remember. The 06 Olympics, I would have guessed with 06. They lit the torch with a parabolic mirror. Now there's one, David, to show your point. See where her torch is? Right there. And she's backing away from it because it's so freaking hot. But it's a very steep parabola compared to the other ones. So she doesn't have to hold the torch way up here. Maybe they should have. Maybe it would have been easier for her. Burn her face off, burn her eyebrows off. But the focus is down here. Pretty cool, huh? I didn't even know about that. Somebody told me about that. Totally rad. Here's another use, not using light, but using sound waves instead. Using sound waves instead. Okay? So the idea of this, and this happens in NFL games, right? With the dancing on the field, right? So you get the sound coming in, and then here, there's your focus collector right there. And again, not quite as shallow as the other ones. The focus isn't out as far. All right, now, the beams or the energy waves, whatever, the sound, light, whatever it is, don't have to be coming from the outside to a focus. They can also start at a focus and go backwards to the parabola and then go forward. That's how newer car headlights work. I think that's how car headlights have always worked, actually. It's just that the focus now is an LED or an HID, where it used to be a halogen or whatever else they used to use back in the day. So if you look at your car headlights sometime, I wish I had brought it down. I'll bring it out when we do the bike. My bike headlight is like this. I got a little 1,000 lumen torch on my. I know I don't want to get hit, and I like to see where I'm going. And there's a great little parabolic mirror inside of there. And the LED lights up, fires the light back. Whew. Now, it's not perfectly parallel on mine. It casts a bit of a wider beam, because I want that. I want a kind of a washing beam versus a pencil point, because I want to see, like, the car that's going to hit me over here before he hits me. Yeah? Cool? There's a headlight. That's one application. There's the old headlight I used to have. That's the 1,000-watt HID before I went to LED. So you can kind of see the parabola right in there. And they've got it patterned. The pattern, I believe, makes noise in the light, which actually makes the light more usable to the... Like, pure sound and pure light, I think, are too harsh. If you hear a pure sound tone, it's actually awful. It's like, and you have to like make it distort. It's weird. If you ever Google pure sound tone, it's kind of awful. You have to kind of make it imperfect to make it listenable. Yeah, Mike.
So is that why they have ridges on a speaker?
Possible? I don't know. Maybe to smooth it out. Or because it moves. I don't know. I don't know. Good question.
Like pencil strength.
But you wouldn't be putting pure sound through your stereo. You'd be playing your music. I don't know the answer to that, actually. That's acoustics, which is outside of my realm of anything I know about other than I like punk rock. All right. David, here's your definition. That's an algebraic display of the... So there's your focus, here's your directrix, here are the equal distances. So that's what a parabola technically is that set of all those points equidistant. It's also used in other places. You might recognize this with the watermark, because I stole it from Howard, whoever that is. That's your Golden Gate Bridge. Now, when you string up a suspension bridge like this, the cables hang in a perfect parabola. As soon as you apply tension to them, they change slightly, become what's called a catenary, which is something that's equally freaking cool. But there's another, suspension bridges are fairly common. Everybody recognize this one? It's been in the great state of Delaware. Don't want to brag, longest twin span suspension bridge in the world. Don't want to brag, Delaware, New Jersey. Nobody's impressed. It's okay. It's okay.
My gosh.
But your daughter's been there.
Yes, she just went to New Jersey the other day and she just sent me a picture. Isn't this a double decker?
No.
Okay, never
Sure, she was in New York or in New York?
She lives in New York and she's going to New Jersey.
The double-decker bridges are from New York to Jersey. There's the, what the hell? Yeah, it's not this one. This one's down southern Jersey into Delaware.
She said it's very scary.
Oh, it's awesome. It's freaking awesome. The engineering of bridges is ridiculous. I remember hearing when the Golden Gate was being built, this is freaking unbelievable. This is where estimation does not work. You don't want to estimate a bridge because you get a bridge like this. So the engineers that put this bridge together had calculated within 30 seconds or something of when, because you see, when they build bridges, you've seen how they build bridges. They start on one side and the other and they meet in the middle, which makes perfect sense. You kind of have to do that. When they were laying the roadbed of this bridge down, they calculated within 30 seconds of when the last plate was going to drop in, and then they have to bolt it together to make it rigid. But here's the cool part. They also calculated where the sun was going to be right then and the expansion of the metal. So they dropped the plate in, and seconds later it expanded out to meet the other place, and they bolted it right then.
Wow.
I mean, that is freakishly intelligent. I mean, it's exactly showed. I shook my head. I'm like, oh my God. It's all physics. I mean, it's all predicted. But to foresee that, that's the part I would miss. I would miss the foreseeing of having to do that. I would be like, oh, the sun? What's that got to do with anything? Well, everything. Yeah.
You know it's not supposed to be red.
It's not supposed to be red?
Paint that they use reacted to the salt water and just turned it red.
But what color is it supposed to be?
It's supposed to be gray.
Gray! It's so much better this way. It's so much better. I remember after 9/11, all the guards in their desert camo standing on top of this thing being like, did they not get the memo? It's orange? Yeah, I mean, yeah, I love the color. I think that's part of the beauty of it, is that it is that color. I did not know that. Thank you. Thank you. Now, there's also some interesting engineering that goes into bridges when you build them wrong. Maybe you guys have seen the Tacoma Narrows footage from back in the day when they built the bridge. Bridges have a natural oscillating frequency, like a guitar string. When you play a guitar, the impure tone you're hearing is the oscillation of the string, and there's certain harmonics. Well, this Tacoma Narrows bridge actually had an oscillating frequency that the wind coming across it created. It turned it into a guitar string. And there's a great old school video of the bridge actually beginning to oscillate, and then it just breaks because it can't handle the load of it. But it went for a long time before it broke. There was a car on it, and there's a video of a guy running off away from his car.
I used to drive across that actually a lot when it would do that. It was like one particular bad day with that actually.
Yeah, well, exactly. But the wind was just at the right speed to generate that frequency. You probably noticed that if you've ever hiked at Smith Rock, the bridge that's at the bottom of the main trail over the water oscillates from people walking on it. It's a bit suspended. It's not suspension like this, but there's a suspension mechanism in the middle of it, and if you get going at the right frequency, you actually feel it go like this. I mean, not to anywhere near as crazy as that one.
And
Go
it's
there.
those things that they put at the parks where the kids can
Exactly, just like that, just like that. Although the problem is, those aren't caught by the wind like these bridges across chasms are. That's when you have to engineer that not to do that, basically. Yeah, make sense? So we care about parabolas, and we care about parabolic motion and parabolic kind of, but the question is, it goes back to Linda's point, when do we actually get parabolic data? And here's the thing, you're not always expecting it. Sometimes it just happens. But one of the places you do get it is via gravity pulling on Earth. If you drop something on Earth, the longer it falls, the further it goes. I mean, that's pretty understandable to a terminal velocity. So if you're standing on top of a cliff and you drop a rock, it might cover 20 feet in the first second, but it's going to cover more than that in the next second, and more than that in the third second after that. And more is a relative term. It's actually predictably more. So what I'm going to do is I'm going to go upstairs, grab my bike. We're going to head outside, and I'm going to position you guys out to collect some data that I think will be parabolic. And we're going to come back in if we have time today. If not today, we'll do it on Monday. And we're going to plot the data and see if we can see the parabola kind of arise. So here's what we're going to do. I'm going to use the hill, I think we're going to use this hill out here. I was scoping it out the other day. I wanted to do one that's steep enough to get interesting, but not so steep that I die. So I'm thinking if we use the one that's out here, we'll go the wrong way. You know what? Let's do this. Just go out the steps towards Juniper Hall and hang at the top of those steps, and then we'll look at both of them. We might want to go the right way so I don't inadvertently kill myself by running into an oncoming car. Let's go up to the top of the steps towards Juniper Hall and just meet me up there. I'll grab my bike.
Do you need to